Hello, everyone. My name is Ana Trišević, and I am a research scientist at MIT FutureTech. I'm going to introduce our next speaker. Our next speaker is Yilun Du. He is an assistant professor at Harvard with 2 appointments at Kempman Institute and Computer Science. He received his bachelor degree and PhD here at MIT, and he was previously a research fellow at OpenAI, as well as intern and visiting researcher at FAIR and Google DeepMind. His research spans generative models, decision-making, robot learning, and embodied intelligence, with a particular focus on building agents that can reason, plan, adopt in the physical world. His early work in energy-based models helped lay the foundations for diffusion models. And even now, he does research that help us think about generative AI and applications in science in robotics. Yilun has had an incredible, productive career already, and we are very excited that he has chosen to stay here in the area for his tenure track journey. So please join me in welcoming Professor Yilun Du.
Okay, good. Yeah. Thank you so much for the introduction. And today I'll talk a bit more on the AI side about how what we can do with current AI tools, in particular world models. So I guess we've, over the last several years, we've all seen how powerful large language models are. So if we ask different text questions like how do we build AI with the language models, they can give you these step-by-step instructions. But a lot of the tasks we care about in the physical world, where we actually want to manipulate or interact with the world, these tend to be tasks that these current large language models are pretty poor at. So even if you have a pretty simple image where I give you 2 balls and ask you, how do I manipulate one ball to the other ball, the model just doesn't understand the physics of the scene and just randomly makes some guesses. So in general, for a lot of more physical use tasks, the current language models or vision language models, they aren't actually very accurate because they just don't seem to understand the physical world very well. So this talk will be about a different approach towards using generative AI to get much more intelligent autonomous agents. And it's about how a lot of these generative AI models, where this one is actually a video generation model, these models, or so-called world models, really allow you to take an input image and allows you to generate realistic videos depicting what you want. So just to play this video again, you can see that just from the first starting image, a system is able to simulate and generate these really realistic videos depicting what it would mean to saute some onions. So what this talk will be about is how we can really use these generative video models as a tool to build intelligent decision-making systems. So I'll give a bunch of examples of how you can use these video models as policies. So essentially as ways of generating videos depicting how a robot should act, as well as then having the robot act based off those actions. I'll talk a bit about how these models can be used as simulators to simulate how the future will evolve. And then I'll talk a bit about how we can really combine them with existing large language model systems to allow them to more accurately interact and learn and do different tasks in the physical world. So first, let me talk a bit about their use cases policies. And the general idea is that you can, if you have a nice text conditioned video generation model, this model can be used as a very effective planner or imagination. So if I want to pick up pick up an object, let's say color it and then place it next to another block, we can use these generative AI tools or world models as a way to synthesize a sequence of images depicting how you solve this task. And the nice thing about these models is essentially you can train a model to solve all types of different robot autonomous tasks. So you can train the same model to also solve this task where it generates a video of placing this object in a box, but you can also have it generate these more realistic videos in real scenes where here you have a real image, and now again this model synthesizes this plan of pushing the sponge over, as well as having the same model pick up silverware and be able to place it down. So in general, these video world models give you a way to really just be able to generate a future-like image or video depicting what you want to solve. And once you have these videos depicting what you want to solve, you can use a separate procedure to just infer the actions from the videos. And this allows you to then convert it into real robot executions, which I'll give several examples about in a bit. And one really nice thing about this is this procedure of training this type of automated video generation model is that it allows you to take advantage of all the video information that we have in the internet. So in the same way that we have so much text data, which has really led to the advancements of large language models, we also have tons of video data. And this video data can really teach you a lot about the physical world and the semantics of solving different tasks. And once we have this video model, this is a bit small, but roughly we have some procedure to essentially infer actions that correspond to those videos. So if you have a very clear depiction of every single state you want to reach, it's relatively easy to get the actions to then reach each state. So let me give a couple of examples of how realistic some of these videos can be. So let's say I want to put a carrot on a cutting board. This is fully synthesized, but you can see that a robot's able to pick up the carrot and put it on the cutting board. Or we can also have the model be able to flip a pot upright in a sink, where again, you can see this video of the model just flipping the pot upright. In general, these video models are able to synthesize very realistic plans depicting how to solve tasks across a variety of different settings. So here, or like with a lot of diversity. So here we have this image on the left, and we want to flip the pot upright in the sink. And now the video model is able to realistically generate each of these depictions of flipping the pot upright. You can also have an instruction, put the big spoon from the basket to a tray. And again, it's able to do this. Or we can say something like turn the faucet on the left, and then you have these generated videos depicting how you want to solve this task. Okay, so let me actually show an example of this, converting this to real robot interactions. So here we've been working on recently a large video planning model, and this is this is a generated video. So we have this image. So we just randomly took this image, and then we randomly chose the instruction clear the tape. And this is fully generated by the model, but you can see that the model is able to imagine picking up the tape and then pulling it off. And now, basically, once you have this video, you can use the visual states generated out of video to infer a set of robot actions, allowing you to have the robot do the same action. And you can see that there are still some control issues with robots. So I would say that maybe things are still a little far away in the future. But you can see that it's pretty generalizable across. I will give quite a few more examples in a bit. So just to give a little bit more technical description of how we get the actions. So one general way we do this is we have these images. From these images, we can estimate the motion or difference in different images. So we can estimate this optical flow. And once we have this optical flow, as well as maybe some type of depth image that you can get from the first image, you can roughly infer a set of actions to change the robot in. And this procedure, so let me just give a couple examples of this. So here, let's say this is a synthetic environment where we want to pick up this object and place it on a peg. And roughly, your generated video depicts this action. From this generated video, you can just look at the difference between the two frames. And if you look at the difference between the two frames, now you get this motion of the robot arm. And then from the motion of the robot arm, it's pretty easy to just code up something that infers the correct raw actions to execute in the environment. And this can be used not only for manipulation, but also if you want to do some type of navigation in the environment. For instance, maybe you want to churn to the left in this image. What you can do is, again, you have these synthesized images. From these synthesized images, you can infer the motion of the scene. And from this motion of the scene, you can then compute the pose transform of the robot to execute in the environment. So roughly, this type of procedure allows you to generalize pretty well across different both manipulation and navigation. And here's just a robot example solving this task. So instead of having a humanoid robot, here we have the robot pick up an apple and place it down. Another thing that you can also do, I'm just giving a couple examples of how we can actually get actions from video models. But another thing you can actually do is even if you don't have this type of motion or dynamics to infer the actions, you can actually just use interaction with the real environment as a way to get models that can actually convert videos to actions. And the overall idea here is your video model just generates a goal for you. and then you have a separate controller that tries to reach that visual goal. And whatever actual environment state the model reaches, you just add that to your replay buffer, and you use that to refine your goal condition model. And by repeating this process of using the video model as your goal, trying to enact that in the physical world and seeing where your robot actually goes, you get a continuous stream of data for training a model that can go from your current image and the next image and infer the intermediate actions. So this allows you to actually take a video generation model and deploy it on any type of robot, even if you don't have any of this depth information, by simply just interacting with the environment. So here's just a quick example of this. So we have a synthesized video here. And then so we have no action data at all. So it's just a new robot. We haven't seen it before. So at the beginning, when you try to control the robot, it has no idea on how to reach this video state, since it just doesn't have any action data. But by just like deploying the model, running your policy a couple of times, eventually it's able to, so this is after 50 rollouts, it's able to do this task much more accurately. And then afterwards, you're able to, after a lot of interactions with the environment, you're able to very reliably solve this task. So in general, you don't necessarily need action data. Just by exploring in the environment, you can actually get a pretty good model that can enact your videos. So now let me give a couple more examples of like how powerful the current video generation tools are for just planning or synthesizing the images that you want to do in the future. So here, this is given this starting image, this is a generated video for inserting the straw in the cup. So you can see that it's actually able to pretty reliably simulate moving the straw inside the cup and placing it down. And one thing that's interesting is you can actually nest these actions. So again, given the same as that first image, one thing you can do is you can say, now I want to insert the straw into the cup, and then I want to push the cup closer to the mouse. And now if you look at this video, we're able to do this. And then imagine what would happen if we would push it to the mouse. So these systems are actually very realistic at the current moment for simulating these physical interactions. Here's another example. So here, we want to place a blue block on top of the red book. So all of these images were fairly non-curated. So what we did is we just asked a couple of people who are unrelated to our paper to gather 100 images of their household. So these are the images. But here we have the instruction, place the blue book on top of a red book. And now it's able to, so now you can simulate picking up the book and then taking the book and placing it down on the red book. So if you look closely, you can see that the physics isn't perfectly accurate. There's a bit of a motion, but you can see that based off how realistic these videos are, it's not hard to imagine that you could get a robot control system that can then convert these videos to actions. One nice thing about this procedure is that it allows you to control the world in a pretty flexible way. So here, if we have the instruction, put the Coke can on a green cube, it's able to do that. But we can take the exact same scene, and we can say we want to put the green cube on top of the Coke can. And now it's able to do this procedure. And you can also have say something like put the Coke can on the Mentos, and it's able to do this. So these models are pretty controllable, given the starting image. They can allow you to simulate all types of actions. And now let me just give a couple more examples of actually taking these real videos and actually having a robot actually do them also. So here, this example is we want to press the button. And then from that generated video, here we infer the actions, and the robot is able to correspondingly press the button. It's a much slower because it's still right now, I think there's some bottlenecks of controlling robots, but you can see that eventually it goes up and presses the button. Here's another example. So here this is generated, where here, given the starting image, we have the instruction, spread the coffee beans. So you can see that, again, there's a little bit of physics issues, like the beans kind of go through the bag. But like you get the rough motion is there. So if you convert it to robot and you ask it, I want you to spread the coffee beans, here's the corresponding execution. It takes a bit of time for the robot to appear. Okay. So one thing, so the videos are fairly slow, but these are real-time videos, so we have not sped them up at all. So this is approximately how fast it would actually happen in the real world. Okay. Great. Okay, so that was the first part of the talk. So I talked a bit about how we can imagine these video models as policies. So essentially having these models just generate videos depicting what you want to do, and then having a separate model that converts these videos to ground truth robot actions. So the next part of this talk will be about how we can really use these like powerful like world models or video models as a way to really build simulators of the world, and how we can really use these for intelligent robots. So one overall idea is that it turns out these models are pretty good at simulating real-world interactions. So this was a while back, and now with things like Sora or VO, we see much more realistic videos. But but what we can do is we can take the starting image here, and we can 1 second. So we can take the starting image here, and we can simulate all types of actions on the starting image. So here I have this image here, and what I can say is I want to simulate washing my hands. So the video model is able to simulate you washing your hands, and then it's able to simulate you washing the bowl. So you can essentially, given a starting image, you can just, in a pretty freeform manner, just simulate different sequences of actions on top of it. So given the same starting kitchen scene, you can do all types of things like washing your hands, cutting carrots, washing the cutting board, or washing carrots. So essentially, one nice thing about these models is that they just allow you to simulate all types of physical interactions. So why does that matter in robotics or automation? Well, here's an example of what this allows you to do in a robot. So this is fully simulated from the starting image. And you can essentially just simulate a pretty long sequence of events. So I can put the can on top. I can close the bottom drawer. I can now open the middle drawer. I can put the orange in the drawer. I can close the drawer. I can open the top drawer. And you can imagine, and essentially you can just continue to roll out this trajectory in your mind. And so why is this useful? Well, what this really allows you to do is now one really big issue was trying to train different types of neural network models is that oftentimes in the physical world, it's really hard. It's really difficult to run these models in the sense that when the models are very poor, they might break things. They might break the table. They might hit something. Maybe you have to consistently reset the scene. It's hard to get many parallel environments. But by having these powerful models that can actually simulate these pretty long horizon interactions in the world, now you can directly train your systems that you want to deploy in the physical world entirely in the space of the model. So here are these some of the simulated rollouts in the space of a simulated model. So the model is able to simulate all these actions of pushing blocks. And what this allows us to do is we can just train a policy entirely in simulation. And now we can just deploy this policy in the real world. And it's able to do different tasks such as pushing the red blocks towards the blue cube or moving the blue cube next to the green circle and so forth. So this gives you a powerful way to essentially train things entirely in the space of your imagination. Another powerful thing that this type of dynamics model gives you is that when you're actually trying to control a robot, you can also use such a dynamics model to actually control the robot. And the idea here is now given a starting image, what you do is you just simulate a set of future states. So here, what we did is given this image here, we just simply guess and randomly simulate a set of actions. So we make a total of 5 or 6 different guesses of actions to do. And what you can do is now you can have the world model simulate what the world would look like if you did every single one of these actions. And based off of the simulation, now you can select the one that is closest to solving your task, which is this one here. And now by repeating this procedure recursively, you can control a robot to specifically solve the task of pushing this T into this area. Now, the benefit of this approach is now you can entirely see what your robot would do in the future. So one issue is, let's say you're doing some types of automation, and now you have all these concerns about safety, where you don't know what exactly the robot will do in the future. So with these dynamics models or world models, you can preemptively get some type of visualization of what the actions of the robot will do, and this allows you to much more safely and robustly get your system to be able to move to the eventual T position. And this is especially useful in tasks where there's a lot of other objects that are blocking your way. So here we want to push this T again into this hole. But the issue is now you have all these other letters that are obstructing the way. So now you somehow need to push all these other letters out of the way. And what you do is after running this procedure for quite a while, you're able to eventually successfully push this T into the target location. So roughly, this procedure of having some type of model allows you to both at training time train entirely in your simulation, and at test time it gives you a pretty useful tool to really visualize what your policies will do, as well as get a robust policy. And in general, these types of world models, so all the examples I've talked about earlier are in the space of 2D, where I'm just showing you a couple of 2D images. But you can actually do this also in the space of 3D. So here, again, we're simulating these things, but now we're simulating these environments in the space of 3D. So here you can see that like for every single interaction, you can actually get a 3D mesh depicting the action. So you can imagine that like maybe I want to be extremely sure that like in the space of 3D, I'm not trying to like squish something or I'm not trying to hit something. Now you can actually generate these simulations in the space of 3D. And the rough idea, just as more technical details, but the way this approach works is it generates some type of RGB image, some type of depth image, and some type of normal image that allows you to get an overall 3D reconstruction. And there's another way to get some of these like 3D models by getting some type of compact 3D latent. Let me just quickly show the results. What this allows you to do is essentially allows you to actually get a very like dense 3D rendering the entire scene. So here, which each of these videos are showing is a single generated state of the world. So now like so by using a much more compact latent representation, your video generation model can actually generate these full 3D scans. So every single time step is this full scan of the scene, but it's able to simulate how you can grasp an object across these scans. So you can not only get like these like mesh-like representations I talked about earlier, but you can actually get these full latent descriptions of the scene also. And another pretty powerful thing about some of these models is that you can actually run these simulations for a very, very long time period. So on the left, this is a Minecraft scene. So you're only given the starting image. And then by running simulations through the model, you can actually simulate this entire interaction in this environment, where the model can continuously move around and keep like placing blocks and so forth. So these models allow you to do very long horizon simulation with some additional technical tricks that are discussed in the papers. Another example is this image here. So given only this image here, we can imagine infinitely traversing this room. So all of these frames are just generated from the starting image, but you can just essentially just continuously move around in this environment for as long as you want. So essentially, you can imagine that these models are also very powerful tools to enable you to just repeatedly run pretty like long horizon simulations to train different models. And yeah, and it just keeps going. So you can just. I mean, one thing that's interesting about these models at the moment, though, is you can see we move out, and then when you come back, it's a completely different room. So there are still some issues with memory and state, but you can just continuously simulate forward. And there's some interesting other work where you can actually add like explicit memory into these models, so it avoids this issue a bit. So this allows you to actually more accurately simulate like entire traverse of a Minecraft world. So there's some work on like trying to improve these problems. But roughly, these models are pretty powerful models for also just simulating how the dynamics of the world will evolve. And the final thing that you can do, so in the last two parts, I talked a bit about how they can be pretty powerful policies, allowing you to generate these visual plans that allows you to get actions to execute on the robot, as well as pretty powerful simulators. The final thing these models are also very powerful at is they can actually be interfaced very well with existing large language models or vision language models to provide a bit more of physical knowledge into these models. And this allows you to take both the strengths of these large language models, which are much more high level as opposed to physical, and combine them with some of these visual knowledge that you have in these video models. So let me skip this slide. But roughly, what you can do is, let's say I have a hypothetical task where I have I have two pieces of fruit on top of this cabinet, and my goal is to put all the fruits in the on top of this cabinet into the top drawer. So what you can do is you can initially just ask a VLM to generate different actions to solve this, and the VLM might say things like place the banana in the top drawer or open the top drawer. But one big issue with VLMs is they don't really understand physics. So they actually don't know which of these actions is good, right? So if you directly just use the VLM, you'll have some issues with these types of tasks. But you can now use the same video model that we talked about earlier to simulate what would happen. So for each action the vision language model generated, for instance, if it says put the banana in the top drawer, the video model will just simply simulate that. And because there is no top drawer, it simply just drops the banana. And in contrast, when you ask it to open the top drawer, the video model is now able to reliably open the top drawer. And now once you have each of these video plans, now you can use the VLM to assess how good each of these plans are. So if you have a plan where you take the banana and simply drop it, well, the vision language model isn't very good at like understanding the physics of what would happen if it were to actually just pick up the banana itself. But given the final image, it can tell that this is not a good state. The VLM tells you that this is not a good action. And in contrast, for the action here where you open the top drawer, well, the VLM sees the last image and says, this seems like a good action. And this allows you to find the right action to take in the environment. So over time, this allows you to really plan in the space of the VLM's imagination to solve this task. So if I want to solve the task, put the fruits in the top drawer, well, so at the beginning, the VLM generates two actions, which is either open the top drawer or place a banana in the top drawer, which are the two examples we've talked about. And we just select which one is most promising, which is the first one. And now, given the last image of that generated plan, we simply just repeat the procedure. So the VLM now generates a new action, place the banana in the top drawer, and again, it assesses how much progress there is. And here, there's a bit more progress. And now, from that new image, you then again repeatedly simulate possible actions in that new state until you get an overall plan for solving this task. And this procedure of planning across all of these models now allows you to get this corresponding real robot plan of solving this task. So of opening a drawer, placing each of the pieces of fruit in the drawer. And yeah, closing the drawer. And here's another illustration of this. So here this is the robot actually autonomously solving this task. So one thing that's interesting is in this setting here, neither the video model nor the vision language model are specifically trained on this task. But actually, just by zero-shot doing this planning procedure, now we can get a system that's able to effectively solve this entire task of placing the fruits in the drawer. Just to give an example of what the system, what this type of planning between both the video model and vision language model can do. Here we have a goal where we want to take all these blocks and we want to arrange them in a line. And this tends to be a task that the VLM is not that great at because it can't really predict the precise dynamics of objects with respect to each other. So it will say high level in statements such as push the yellow block forward or move the blue triangle to the left, right? But if the language model just gives these very high level specifications, there's no way you can actually make a line because you could push it forward here, or you could push it over here or here. Like there's a lot of ambiguity. But by doing this procedure of having the vision language model generate some language plans and having the video model simulate the effect of each one and selecting the most promising ones, now you can get this completely synthesized video here, where the robot is able to very precisely push objects so that you can eventually get this entire plan. And then you can also convert this to real robot execution. So now this is a real robot doing it in the space of imagination. It's a different scene, but the robot is similarly able to convert that imagination to reality. And another thing you can do is you can also do something on the flip side. So for a lot of tasks that we want to use generative AI in, they involve things such as spatial reasoning or physical reasoning, right? So maybe I have this image here, and I want to say, if I sit on my couch on my right and I face the chairs, like which direction is the kitchen? Is it on my right or is it on my left, right? Like how can I reason about where I am in this scene? And it turns out that these vision language models, when they actually have to reason about the physical world or have to reason about space in the world, they get very confused because they don't really, this is not a thing that is very available in the language space. But what you can do is you can use this type of world model as a way to help you do this. So what you can do is you can imagine different interactions in the world in the space of the video model, use these interactions as additional context to give to the VLM, and this allows the VLM to reliably answer these spatial reasoning questions. So here's a graphics description of this. So I want to, if I sit on my couch and face the chairs, is the kitchen on my left or my right? And what you can do in this setting is you can have the video model take the robot here and have it imagine different simulations of what it would see if the robot was rolled out from this starting location. And now, given all of these simulations, which are these videos shown here, we can simply take these videos, give the video as context to the VLM, and then the VLM is able to take these helpful video generations and use it to accurately. So this is a video rendering in the world that actually was simulated, and it can use this to very reliably solve these spatial reasoning tasks. So here's a couple other depictions. So roughly the action space for these models. So this is a pretty simple setting, is like turning left 10 degrees, 20 degrees, 30 degrees, moving forward, or turning right. But here's an example of what this enables you to do. So here we want to ask the question: if I'm at the screen point and I'm facing this bottle, will the whiteboard be on my left or right? And this is really, so this type of problem is a type of problem that's just very challenging for VLMs if you just try to input them. But what we can do is now we can have a video model just simulate different possible interactions in the world. So first, the video model might simulate what would happen if you moved forward 75.75 meters, or turn left, or turn right. And then from each of these interactions, we can just choose the one that seems to be the most promising one. So we take the rendering that was most promising, and then we try to simulate some additional movements in the world that can be more helpful for helping the VLM solve this task. And then by repeating this process over time, eventually we get this overall sequence of actions that allows us to solve this task. So it's still rendering a couple possibilities right now. But yeah, eventually what it finds is that this overall video, which depicts you moving forward, turning left, so moving forward, going over here, and then looking at the right. From this image, it's very clear if you're at the green point where you're facing the bottle, that the whiteboard will be on your left. So essentially, this procedure allows you to find the right way to view the world for your VLM to solve your task. And so we actually compared this across a variety of different vision language models, such as GPT, O1, or Gemini. And what we find is that, in general, when you add these world models or imagination, this allows you to much more reliably solve these spatial reasoning tasks. So overall, in this talk, I've talked about how we can use video models as accurate planners or imaginations, where, like, given a task, we can have the video model generate the video, and then from that generated video directly make a policy to act in the environment. I've also talked about how we can use these like world models as simulators to both train your policies purely in simulation, as well as use them at test time as a way to select promising actions. And finally, I've talked a bit about how they can be used as a tool to be combined with powerful language models to solve more physical tasks. Thanks everyone for listening, and I'm happy to take any questions.
Wonderful. So I wonder if I can start out by trying to understand sort of where this advantage comes from, right? So you can imagine do a planning process for a robot and saying, oh, I'm just going to do that. I'm going to simulate lots of different ways to do it. But I guess it's a pretty hard optimization problem. There are lots of constraints that you might want to take into account. Whereas these video generations, they're sort of based on videos from the real world that they come from. And so you sort of know that whatever action is happening in those videos is like allowed by the world. And so is the big thing we're doing basically constraining our space for the robots to say, like, because we can predict what can happen in the real world with fidelity because of these video generations, now we can use that as a guide for these robot control policies that makes that problem, is it just like much less complicated in optimization? Is that where the benefit is coming from?
Yeah, I think that's a great question. Yeah, so I think it's, mainly these video models have been trained on all of these real videos of humans solving tasks, so you have all these demonstrations. So yeah, it severely reduces the search space you need to search for to get good actions, because now, so first, like, a priori, if you just have like a system without any of this knowledge, like if I ask it to like maybe make dinner, it has no idea what the steps are to make dinner, right? But now, because it's seen all these videos of how people do it, it now knows all the relevant steps. It also knows the relevant real-world physics. So it really reduces the overall search space for getting actions like you mentioned.
Wonderful. Okay, questions?
Yeah, thanks so much for the great talk. Very inspiring. And it looks also very promising. But I also wonder, what I like to pitfalls, but also where are like maybe like some use cases where you say like purely with like simulation and video is maybe like not sufficient enough, and you actually need some kind of real world data through like teleoperation or the robot itself. Is there like, are we gonna see like two different approaches for like a different set of tasks to automate things, or do you think like this like actually like with world models like this is sufficient to basically automate like most of the tasks?
Yeah, I think a big issue with a lot of these models, I think I mentioned it a bit in the talk, but maybe I should mention more, is that they are not very physically accurate. So you can see that in several of the videos I've shown, like some of the objects would move through plastic bins, or like sometimes things would hover in. So I think these issues make it so that if you want to do really precise like factory tasks or assembly tasks, it's hard to use these models because they might not actually depict the very precise actions you want to take. So I think in these settings, as well as most settings that you might want to deploy these models, you probably actually want to get a lot of teleop data on the physical robot. And maybe you would want to take the rollouts from your model, try to execute them in the physical world, and use the physical road rollouts as additional data to train these models. So I think you will definitely need a lot of real world data to really get these models to very reliably and physically accurately simulate the world. Thanks.
Thanks for a nice talk. Yesterday, I don't know, IBM, Patrick at IBM, I don't know if he's here or not, gave it, oh yeah, talked about doing procedures in a lab and trying to sort of learn what the steps are before you put them in your notebook. And that's a great, seems very similar to your work. To me, the interesting question is to find out when anomalies happen. So I'm cooking dinner, but the knife falls on the floor or something, you know. So trying to train this to sort of learn, you know, the good things, but also learn the bad things, just sort of seems like you have to look at a bunch of videos or something. I don't know. Can you talk about that?
Yeah, I think that's a really good point. So I think all of these models are really trained only on YouTube videos. And most of the YouTube videos, I mean, they'll show you cutting the things accurately, but they won't show you like maybe you failing to cut the things, or like maybe your knife breaking, or like your glass shattering. So the question, so how can you actually get these models to simulate these settings? I think a lot of it has to be that like you probably need to actually interact in the physical world to get the data for these failures. But yeah, I think like on one hand, if you have these planners, maybe this is not a huge problem because you're just trying to, you probably just want to simulate the good examples. But like if you use these models for simulation, then for sure you want to simulate these bad things. And I think like that's a very important question that is hard to do with the current models. I think it might require a lot of interacting in the physical world to get data to be able to do these anomalous events.
So on that last point, in terms of interacting with the physical world, how confident are you that that these systems can be useful for AI automation in terms of the hardware being up for interfacing with them? So how ready are we in terms of interoperability with different types of robots in the field?
Yeah, I think hardware is a pretty big limitation also. So if you actually look at some of the examples I showed in the policy portion, the hand is shaking, and we found that the hand actually broke a lot. So I think that especially if it's like more of a human, like automated mechanical hand, those tend to break very easily. Whereas parallel drop grippers are a bit more robust, but again, there are a lot of tasks that are hard to do with those grippers. So I think hardware is actually a pretty major issue in this line.
I'm even thinking in terms of software interfaces.
Sorry, can you, like in terms of, can you describe that a bit more?
So having models talk to physical systems,
Mm-hmm.
you kind of glossed over it and said this is an easy task to make it done, but there's a big diversity of, let's say, robotic systems in the field. So I'm wondering if you see that as a challenge at all in terms of interoperability of models with different types of physical systems. Is this going to be a blocker at all for AI automation to find widespread use?
Yeah, well, I think for depending on the physical system you use, I think you definitely have to make new design choices to make this system work the best on that particular physical system. I think one nice thing about the fact that you're predicting videos as opposed to, let's say, actions is that the videos are pretty shared across different systems. So you could imagine that this high-level model of generating these videos, it could, as long as you have maybe some additional data in your particular system of interest, it might work pretty well. But then yes, there will be a lot of still low-level engineering and connecting these videos to actions, and then that will have to be per system based. Yes.
Yeah, I'm going to ask a naive question. I'm an economist, not a computer scientist, but I guess I've become increasingly convinced, based on what has been accomplished, that many more things are a big data problem than I used to think, that I thought they needed a model or something. But this seems like maybe it's not a big data problem. Like, you know, this seems so alien to how people do this, right? It seems like we must have a mixture of a pretty good conceptual model of how the world works, and then some kind of computational apparatus that allows us to solve these problems so quickly. And I'm just wondering, and maybe that's not important, right? You know, you care about the results, not how it's done. But do you have any sense of how what you're doing relates to how organisms in the world do this so quickly?
Yeah. So I think I definitely feel like organisms in the world don't like generate photorealistic videos in the future. Well, yeah. I think it's like it's even if you just close your eyes and I ask you to like reconstruct the scene in front of you, you definitely are not able to generate photorealistic details. So yeah, I think in the long run, I feel that so it does seem like for a lot of decision-making tasks in the human brain, you do have some type of mental model of how the world will evolve. But it does seem like the model is not just pixel space. So I think a very, very interesting set. And I think this also goes back to the earlier question on anomalies. I think if we can find the right latent structure and to do simulation in, that would be much, much faster. And also it could allow you to simulate physically implausible, like things you haven't seen before much more accurately. And another point is maybe we don't have a single model, but rather we have a hierarchy of models or of different structures, right? So you have some models that are very high level that allow you to plan very quickly. And then if you need to have very precise actions, then maybe you have a cascade of models that become increasingly more accurate. And maybe this model is like the most physically accurate one that you would only use at the very end.
So let me just build on that for a second. So I am curious if you think about the quality of results you get. If you compare, like if you doubled the amount of data you had, right, versus if you used a more powerful video generation model or something like that, like what's your sense of like how much extra gain do you get when new generations of video models come out or things like that?
Yeah, well, I think I guess if we look at how the video models have come out, right? Like I guess there's been like a VO3, there's VO2, VO1, and then there's Sora before that, right? The quality is actually increasing quite rapidly. I think that when you increase the size of the models, it seems that you get quite a bit of a boost in physics and accuracy. And I think in terms of data, actually, I think most models currently are using a very, very small amount of the overall data in the internet. I think you get a pretty big boost both from data as well as the model size. I think neither are very close to saturation. I don't know the exact proportion of gains, but I would say that, well, in contrast to like language models, I think there's a lot of room to grow both on the data side as well as the model size side.
Yeah, no, and I'm sorry, I should have been more clear. So, right, so I totally agree that the video models, precisely because the scaling laws are doing better and better. I guess I'm curious, like, you're sort of a downstream application of that, right? And so if these models get like vastly better, as we've seen in the video models, like, do you see the robot actions get similarly better, or like, is that, you know, also getting large scale, or is that sort of a slower gain if you go compare?
Oh, I see. Yeah, So I think in the robot action space, yeah, I mean, honestly, at this point, the videos are already accurate enough. I think there are some issues where it's sometimes the models don't pay attention to the actual language instructions you ask them to do. But as long as the semantic following is accurate, I think the video, like even if the video resolution gets much better, I don't think there would be too much of a gain. I think now it's all about like how do you design the system that can map these images to actions, and I think that is a separate problem that I guess is more like robot specific.
Wonderful. Thank you very much.
Yeah, thank you.